What kinds of defects are formed and how are they characterized in terms of distribution, size, and type? What is meant by a defect-rich hard carbon material with multi-stage porous structure, and how do these pores vary in scale, micro-meso-? Macropores. How does this hierarchical porosity benefit sodium ion storage and transport? How do unpaired electrons from nitrogen and phosphorus dopants provide adsorption sites for sodium ions? Can Davis Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? What is the role of these unpaired electrons in promoting structural distortion in the surrounding carbon layers, and how does this structural change enhance the stability of sodium-ion interactions? Do these dopant elements also participate directly in sodium storage reactions as pseudocapacitance sites, and if so, what is the mechanism of pseudocapacitance in this context? How does nitrogen and phosphorus co-doping compare to single-element doping in terms of creating defect sites and improving sodium storage performance? What specific improvements were observed at 1,500 degrees Celsius calcination temperature, including the reported 63% increase in capacity? How is capacity defined and measured in the study? And what are the baseline and enhanced values? What does the approximately 62% increase in initial coulombic efficiency signify in terms of battery performance? And efficiency. How do pore defects created by high-temperature impurity dissociation facilitate sodium-ion storage and transport? What experimental methods or theoretical models were used to elucidate this intrinsic mechanism? How reliable and reproducible are these results across different samples and testing conditions? What advantages does the gel template method offer over other synthesis routes for producing high-performance sodium storage carbon materials? How scalable, cost-effective, and environmentally friendly is this method? What potential applications could benefit from carbon anodes designed using this approach? Are there implications for commercial sodium-ion batteries? And what further research or development steps are needed to translate these findings into practical devices? Overall, how does this study contribute to advancing the field of sodium-ion energy storage? And what new directions does it suggest for future materials design and optimization? What does it mean that in situ nitrogen and phosphorus doping was performed by a gel method? What is the gel method in this context? How does it work? And what are its advantages over other synthesis techniques for doping carbon materials? How are nitrogen and phosphorus precursors incorporated into the gel, and at what stage of the process do they become integrated into the carbon structure? What conditions such as temperature, atmosphere, and reaction time are necessary to ensure effective in situ doping?